Welcome to lecture 20. In the last lecture, we had studied some very important parameters or aspects of compressibility. From the odometer or consolidation test, we have defined A sub V as the coefficient of compressibility. Then we had M sub V, which is the coefficient of volume change. Then we had the constraint modulus, which is equal to inverse of MV. This is very similar to the modulus of elasticity. Then we plotted void ratio with log effective stress, so that we got Cc, the compression index, and Cs, the swelling index. When you unload, you know how much strain it will come. Then we also looked at one of the most important parameters of the soil, which is the maximum past consolidation stress. The soil remembers what it went through in its geologic history, and this you can determine using the simple construction given by Casagrande in somewhere 1936-37. It has become standard now, part of the code. You can find out from the curve P versus log sigma. This is what we call first time compression or virgin compression. This is called unloading, and this is called reloading. And as you can see, this curve and this looks similar, so we say this must be reloading, and we try to determine the maximum pressure by drawing a tangent here, a horizontal line, angular bisector, and extending this line, and you get maximum pass pressure from this simple construction. And once you determine the maximum pass pressure, we define another parameter called OCR, over consolidation ratio, which is equal to P dash C by P naught prime. This is the current effective stress in the sample at the depth from which you have taken it out of the ground. This P dash C is what we have determined from the consolidation test. And OCR generally can be greater than or equal to 1. If it is 1, we call it normally consolidated soil. Usually we say NC. Greater than 1, it is OC. Normally consolidated, over consolidated soil. So you have a variety of situations where the soil can be experiencing whatever it is experiencing now is the maximum in its geologic history, or the current stress is less than what it experienced in the geologic past. If that is so, you have some difference in estimation of settlement, strength, etc., which we'll see in the next class. What I would like to now study would be, why does it take time for the settlements to occur or the compression to occur? You have seen that you have to take readings with respect to time. All other materials, you apply the load, you expect the settlement or deformation to occur. We have a very interesting phenomenon called consolidation of soils, which is a very significant one for fine-grained soils. Fine-grained soils, it's a very, very serious problem, significant if I say, whereas for coarse grain, it is not significant. Suppose I take the sample or a stone, apply the load. Suppose I increase from 25 to 50 kPa, and you put the dial gauge here, because here again you have the filter paper or a stone. The dial gauge readings, in case of sands, you can expect all the settlement to occur in about 10 to 30 minutes. And after 30 minutes, there will be no change in the reading, which means whatever settlement has to occur, it has occurred within the first few minutes. In case of silts, maybe it will take to 1 to 4 hours. Suppose I have a clay silt, sandy silt, etc. It will increase, the deformations will increase, but they will stop after 4 hours or 5 hours. But in case of clays, they go on to maybe 12 to 24 hours in case of very fine soils like clays. Why does it happen? You know that permeability of clays is very, very low. Sands are maybe 10 to the power of minus 2 to 10 to the power of minus 4 centimeters per second. Silts may be 10 to the power of minus 4 to 10 to the power of minus 6. But clays are less than 10 to the power of minus 6 centimeters per second. The permeability is very, very low, which means the water cannot escape fast enough. So it takes time for the water to escape from this saturated sample. And unless water goes out, it cannot compress. And that is the reason why you have a phenomenon called consolidation. Consolidation is reduction in void volume due to expulsion of water under static or dynamic. Static loading most of the time. You may get occasionally dynamic loading, and it is very different. Please remember the term we have used is consolidation. A similar term you probably have used earlier was compaction. Compaction is a process where you have reduction in void space due to what? Is it due to expression of water or expulsion of air? You agree? We have removed the air and not water. Due to, and how is this achieved? By compacting, which means you have dropped the hammer, so it's a dynamic loading. Please remember, these two are very different phenomena and you should not confuse one with the other. Compaction is on soils which we bring in, fills, we engineer them so that I can compact them as dense as possible. Consolidation is a phenomenon which occurs when you construct something on the ground or in the ground and increase the load on the ground by the new facility. It could be a building, it could be a factory, it could be a bridge abutment, it could be a liquid storage tank, whatever it is. When I have soft soil here and I construct something, because of this load, the water from here will try to escape, and that leads to the phenomenon of consolidation. Whereas compaction is removal of air and the densification that follows from there. To illustrate this phenomenon, we have a very simple analogy for consolidation. Take a cylinder with thick walls, fill it with fluid, and I have a small spring here, and I have a piston. This piston just fits in, there is no gap between the cylinder and the piston, so this is a very smooth one, but very no gap. This fluid could be water, oil, whatever it is. You agree, compared to the spring, the fluid is incompressible. You cannot compress fluids because they are all made, say, with molecules very close to each other. So I can say this is incompressible fluid. You have filled the cylinder with some fluid, water, oil, whatever it is. Piston is put on top. Let us say now add a certain weight. I put in, say, 10 kg. I put a weight of 10 kg on the top of the piston. Can the piston come down and compress the spring? If it has to come down, the fluid which is surrounding the piston has to go out. If the fluid does not escape, there is no way the piston can come down, which means the spring is not compressed. Whatever load you have put in goes to the fluid. Again, this is where you have the effective stress principle. Now we'll make it increments. So if I increase the total stress, if the piston doesn't go, the spring does not compress, which means it cannot deform, and all the applied load will go to the pore pressure. So this is what happens. Delta U is equal to delta sigma. Delta sigma prime is 0 at t is equal to 0. At t is equal to 0 means at the beginning of the experiment. If I have an incompressible fluid which is like water, and you are now applying a load, and spring will deform only when the piston goes down. Let us say now you make a hole which is about 1 centimeter. The diameter is 1 centimeter. Immediately the fluid will flow, and once the fluid goes out, the piston will come down and the spring will get loaded. So what happens? Usually delta U decreases and delta sigma prime increases. And finally delta U becomes 0 and delta sigma prime becomes delta sigma. All the applied load will get onto the spring and the spring will compress. This is what is happening in the odometer. You kept the load, you have been taking readings at quarter minute, 1 minute, 2 1/4, 4, 6 1/4, etc. You waited for 1 day, which is 1440 minutes. And you then realize the compression is over then. After that, the settlement or the default dial gauge reading does not change. If it does not change, all the load has gone to the spring. In this case, this is nothing but soil skeleton, which is compressible, and this is nothing but fluid is giving pore pressure. Suppose instead of 1 centimeter, you make the hole smaller. I only say 0.5 centimeters, 5 millimeters. Obviously, the amount of water that goes out will be slower and the deformations will take a longer time. You reduce the diameter to 1 millimeter. The diameter of the hole is only 1 millimeter now. Water will take a much longer time to go out of this, so it takes much longer duration for the settlements to be over. Just to give you a plot, sands, silts, and these are clays. You can see sands will settle within the 10 to 30 minutes. Silts will finally attain the final settlement into 1 to 4, 5 hours, whereas clays will take a much longer one. And that is the principle of this consolidation. And this is called a spring cylinder analogy. The spring is the soil skeleton and the fluid here is the pore pressure. So applied load initially goes into pore pressure and the pore pressure dissipates and it gets transferred to the effective stress. The total stress is always constant. Please remember, you have put in a weight of 10 kilograms or whatever it is, or maybe 50 kPa. Initially, that 50 kPa goes straight to the water, and as time passes, pore pressure decreases and the effective stress increases. So again, you can plot in a simple way to illustrate. During consolidation, applied load is constant. We call it, another word is monotonic, means constant with time. If I plot the pore pressure, U, if I plot now the effective stress, or let's say delta U, delta sigma prime, please note that at t is equal to 0, effective stress is 0. As t tends to infinity, because U is 0 as t tends to infinity. So if I now plot, say with respect to time, settlement, settlement is initially 0 at t is equal to 0. It increases and over a long period of time it may remain, finally attain the final value. So in case of fine grained soil, this is a very serious problem, because whatever load we put in, whatever we construct, will cause settlements after 5 years, 10 years, or even 50 years. You need to find that out, and so we have what is called as consolidation theory by Terzaghi, which is the starting point for our subject. He came with this in 1925, and that is how we now study soil mechanics. So one-dimensional consolidation theory is given by Terzaghi, and a very important aspect or theory for our subject. What he said was, let us take a relatively thin sample, say H2. The properties are constant, like permeability, coefficient of volume change, etc., or even void ratio are constant. They do not change significantly, either with time or distance. That means whatever property you are looking at is the same all over, and they are the same at the beginning and end of the test. Third, the sample is thin, small deformations. 4, linear E sigma plot, etc. You can write a series of assumptions that we have, but basically it is a simple theory and with some series of assumptions to make it convenient for us to analyze. The starting point for this theory is our seepage equation, if you remember, which we have derived as kx delta square h by delta x square plus kz delta square h by delta z square is equal to 0 in the case of steady state C, which means no volume change. If I take a small element, the flow into the element is equal to the flow out of the element. And if that is satisfied, there is no change in the volume of the element. Let's now simplify this, and I am only interested in the vertical z direction, so this term doesn't come into picture. And now we say this is a transient problem. Transient means it's a function of time, and steady state seepage means steady state problem is independent of time. So can I say kz into delta square h delta z square is equal to rate of change of volume with respect to time, or you can say rate of change of volume means basically change in volume per unit time. Again, here I would like you to remember that we had initially delta x, delta y, delta z, where v is equal to, so which is nothing but the volume of the element. So here I'll write this equation as, can I say, k. Now it's understood when we talk of this, it's vertical permeability into v is equal to delta v by delta t. And the volume is decreasing. So can I put it as a negative sign because the volume is decreasing. Now can I take this to the right so that this becomes k delta square h by delta z square is equal to 1 by, I can even put it as v naught. This is the amount of water going out multiplied by the volume of the element is equal to rate of change of the volume. So let us say 5 cc is going in and 6 cc is going out, so then the volume is decreasing by 1 cc. That's what this says. Basically, I have taken a certain unit volume. This is the rate of change in the volume of the element, or the amount of water flowing out, and this is the rate of change of the volume. It's a very simple transient equation. If the right side is 0, it becomes steady state, which means it's independent of time t. So here, can I say that h is equal to u by gamma w? You know the head. Here again we get thin sample, so the elevation head is negligible, and you are only looking at some applied loading. So can I now write this as k by gamma w into delta square u by delta z square is equal to minus 1 by v naught delta v by delta t. When you say the volume is changing, is it the void volume which is changing, or is it the solid grains which are changing? You agree that solid grains are incompressible, so all our whatever volume which is changing is due to void ratio. So can I say this? This is equal to delta v volume by v naught delta t, which means basically can I write it as change in void ratio with respect to time t. We can simplify saying that because we have defined AV is equal to delta E by delta sigma, can I write this as minus 1 plus E naught delta E by delta sigma prime into delta sigma prime by delta t. Very simple. I substitute for delta E by divide by delta sigma prime, and I get delta sigma prime by delta t. Can I write now? This is nothing but AV. So this becomes minus AV by 1 plus E naught into delta sigma prime by delta t. Now you also have the effective stress principle, which means sigma is equal to, can I differentiate this equation? Does the applied total stress vary with time? We said it's a monotonic loading under constant loading, sigma t. So delta sigma by delta t is 0. So can I say delta sigma prime by delta t is equal to minus delta u by delta t. And once you substitute that here, we get the basic consolidation equation, k by gamma w delta square u by delta Z square is equal to A sub V by 1 plus E naught into delta U by delta T. This is nothing but M sub V into delta U by delta T. AB by 1 plus E naught we have defined as equal to coefficient of volume change, and now we get the standard equation, a partial differential equation, which again is very useful in engineering. Whatever is happening, consolidation is also true for conduction of heat in solids, electricity in conducting medium, etc. The derivative of U, the port pressure, due to the applied loading. So usually U is called excess over hydrostatic pressure. So usually we say excess port pressure. Derivative of U with respect to T is equal to K by mv into gamma W. K is the coefficient of permeability, M sub V is the coefficient of volume change, unit weight of water, and the second derivative of port pressure with respect to Z square. We define a new term called CV, is called the coefficient of consolidation, which is equal to K divided by M sub V into gamma W. So unlike in most metals, etc., you find that in case of soils, the hydraulic characteristics and the mechanical ones are coupled. So consolidation is a mechanical coupled problem of deformation as a function of time. Why does it become a function of time? Because the water has to escape. So now the most famous equation for geotechnical people is the Terzaghi's one-dimensional consolidation equation, which is written as delta U with respect to T is CV into delta square U delta. It's a second order partial differential equation with respect to time T and the second derivative with respect to distance Z. This is called the famous one-dimensional, and you need to solve this. If you want to solve this, because you have a time derivative, you need an initial condition. And what is the initial condition? As we said, this is delta sigma T, it's constant. And what happens to the port pressure? At T is equal to 0, U naught is equal to delta sigma. Initial condition is at T is equal to 0, U is equal to U naught. All the applied load goes to the soil. Then you have two second derivatives, so you need two boundary conditions. So what we look at in the field is that, or in the laboratory, you have this odometer sample, you have a porous stone and a porous stone here. I am measuring Z. Can I say at Z is equal to 0, you have a filter paper and the porous stone. So how long does the water molecule take to dissipate the port pressure? It is at the boundary. So can I say that U is equal to 0 for T greater than 0? The moment consolidation starts, the port pressure here will automatically become 0 because it doesn't have to travel at all. So once it becomes dissipated, port pressure becomes 0. Can I say that the same thing is true? In this case, we'll say 2H naught, for example, at the bottom, because it's also pervious. At Z is equal to 2H naught, U is equal to 0, T greater than 0. What it means is that at the two pervious boundaries, top and bottom, please remember at this point, there is no resistance at all, which means all the flow can take place immediately. If that is so, port pressure becomes 0. Another situation which is commonly possible is when I have a hard rock here, this is clay, and I have sand here. This is pervious, this is impervious. This can be easily simulated because the thickness is H. Look at this. Even if it is 2H or 2H naught, if I take the mid plane, what is the maximum distance a water molecule will travel? From the mid plane, it can go up maximum H naught up or H naught down. So this is the plane of symmetry, and so we say H naught is the maximum length of the drainage path. And that is why we say H naught in case of single phase drainage. All the flow will be upward and there will be no flow. The same solution can be applied to this provided you equate the maximum length of drainage path. Suppose this is 5 meters, 2.5 meters is the maximum drainage path. Here if it is 5 meters, 5 meters is the drainage path. The 2.5 meters single phase drainage is exactly the same as 5 meter two phase drainage. So this is a very interesting way you can look at the problem. So we say, I can show it again in a very simple picture. Various. You can see that even though this is 5 meter thick, 2.5 meters will consolidate by flow upward and 2.5 meters will consolidate with flow downward. And these two are identical. So please remember, you always have to calculate maximum length of drainage path, which is equal to half the thickness and equal to the thickness in case of one phase drainage. Here drainage is only to the top. Here it is from to the top and bottom. So basically a 5 meter thick deposit draining into the top and bottom is behaving exactly similar to a 2.5 meter thick deposit draining only to the top. I think we'll talk of the solutions in the